Hello everyone and welcome to another episode of the Quantum Hidden Champions. My name is Jonas and today we are looking at Xanadu AI, so let's dive right into it. So here we are on their website and it says on-chip error resistance photonic qubits. So in this case we are looking at a company that is doing photonic qubits. Here it also says there's a video about it in a blog article. Then here is another thing. So Quantum Software, they are the company behind Pennylane, which is one of the probably most famous quantum softwares out there. We also see some tutorials here. Usually a very nice thing about Pennylane in particular is that their tutorials, they always have very nice graphics to it. So if you click, for example, on this one here, you see there's like really nice explanations and animations. There's of course some formulism here, and there's also some explanation on how to create these programs. You see that there are like some quantum gates explained here and the qubit operations behind that. So actually I think these are like, from my experience, very well explained tutorials to get started in programming quantum applications. Then we also see here on the quantum side of things the compile with catalyst part. So fully integrated with Pennylane, Catalyst enables just-in-time compilation of entire quantum classical workflows, optimize your programs to run meaningful quantum algorithms. So besides the fact that they have some hardware, which is the qubits or the quantum bits, which work in a photonic way, so with photons, so with light. They have a programming language, which is Pennylane. That's what we just saw right before. That's where you kind of code and implement on your computer the algorithm that you want to do. And now there's this part between the programming and the actual execution, right? So somehow what you're writing in the program, like flip qubit 1 from 0 to 1, that needs to somehow be executed on the actual quantum system. And that is kind of what the compiler is doing. So it's basically taking the program, it is translating it to a machine code. So basically something that the machine can actually understand. And maybe it also does some optimization on the way there. Like, for example, if you do multiple gates in a row that could also run parallel, maybe it finds a way to parallelize that. Things like this, right? And this is basically what Catalyst is doing then. Then you see here this section, collaborate with Xanadu. We see two examples here. So Volkswagen battery simulation and BMW quantum machine learning. So both car companies. If we look through this list here, we actually see at least another two car companies I see right now, which is Toyota and Rolls-Royce. Beside that, there's also institutions like IMAG. We see companies like NVIDIA and AWS as like typical NASDAQ companies. There's also Google. There's NIST, which is another institution. We see Rigetti as another quantum computing company. There's also universities like Harvard University and MIT in here, University of Toronto. Another university is also Stanford here. We see IonQ as another quantum computing company, and Quantinum also on the quantum side of things, multiverse computing. So there's a lot of companies in this list here that we've either heard of before in the context of quantum or that are playing a role in quantum. Okay, that's the starting page. Let's take a look actually at the products that they offer. So there's hardware products, software products, simulators, and educational material. Like for example this video, which is also educational material, but not sponsored by them. Let's look at the hardware very quickly. So we again, as before, this is now photonics. So we are working with light as qubits, so single photons, which are the light particles, so the quantization of light. So the smallest possible units in measuring light is a photon. It's a quantum particle, and that's what's being used here. And you see it with these laser pulses here. They kind of have different elements that can probably change the frequency, because we see it goes from red to blue here. There are ways to couple different photons with each other when you bring them close. That's what these couplers here probably are doing. And there are some other elements. So basically it's like a encoding of something but they don't use electrons as in a normal chip where you have electric currents, but instead they are using light as a medium to do their calculations. Actually, to be more precise, here it also says nanophotonic chip powered by laser pulses. So they have lasers which create some light pulses, and those are being used to do the calculations. X-series, X is the paradigm shift X-series devices, the first photonic quantum computers deployed to the cloud. Powered by laser pulses, the X-series push the boundaries of integrated quantum nanophotonics by demonstrating generation of on-chip squeezed states, so the photonic analogon to qubit, alongside by fully programmable quantum gates and photon number resolving detectors. So this explains how the whole system works. So you have these laser pulses, then you have the squeezed states, which are like the qubits, so the quantum or the quantum bits here, and then you have this fully programmable quantum gates, which basically tunes how these squeezed states behave. So the squeezed state itself is the quantum state, and then with the gates you can manipulate it, and then at the end, using photon number resolving detectors, you can actually measure how many photons in which of those lines kind of come at the output, and I guess that's how you actually measure the whole system state. Key features: program the world's first cloud-accessible integrated quantum nanophotonic device, perform Gaussian boson sampling with applications in chemistry and graph networks, evaluate on-chip squeezing, generate pulse of photons analogous to a qubit, use cutting-edge detectors to accurately count photons at the end of the circuit. There's some information here on how to get started. We see quantum chemistry as one of the highlights that are being highlighted here. There's some information about the availability of the system. So we see it's like Monday to Thursday, 3 p.m. to 11 p.m. UTC. For access to X8, which I guess is like the most current series, you have to reach out to them. That's also an interesting thing, that like this is a system that is not available all the time. So that might be because like it needs some operation, or maybe it is blocked for a certain amount of time for users that are paying for it. I don't know. But that would also be interesting to know here. Let's see on the software side of things, there's Pennylane. We saw that before. This is like a way to program their quantum computer, or to program actually the algorithms. We see here, discover new ideas faster, the definite open source Python framework for quantum programming, built by researchers for researchers. So you can use it for quantum computers, integrate with machine learning and quantum chemistry again. So quantum chemistry is apparently a strong point where it's being used. We also saw that before with the battery project, and the other project was in the machine learning space, and also here it says machine learning. So machine learning and quantum chemistry seem to be the points that they actually target. Minimize time to research. That's probably because of the way that things are being built, and you can also reuse some stuff. Then accelerate performance. Okay. Scale up your research. Use the high-performance lightning simulator backed by NVIDIA Q-Quantum on GPU and the cloud. But it goes beyond. Pennylane will automatically use the best computational methods for your workflow and get up to speed quickly. Quantum computing can be complex. Pennylane simplifies it. Explore our extensive library of demonstrations and in-depth computations to advance your expertise in quantum computing, quantum machine learning, and quantum chemistry. Discover how Pennylane can enhance your research and integrate seamless into your projects. By the way, we see that like quantum chemistry seems to be a big thing. So if you're interested in doing together like a research project, if you want to learn more about that, if you want to play around with quantum chemistry, and you want me to do that and you follow along, then let me know down in the comments below, and we will start a project on this specific topic. We go back to the offerings here. So what else do we have? Catalyst is another one. again, we are changing to Pennylane here. That's like the whole software universe that goes along with Xanadu. So here it's about Pennylane Catalyst. Okay, so that's basically the compiler. It also says something about like how the compiler works. There's also a runtime and a JAX front end. So okay, there's some information about that available here as well. And I will not go into the details for now. Let's move on and look at the simulator. So there's Lightning, high performance quantum simulator, Lightning, designed to provide the ultimate performance for quantum machine learning applications. So this is now targeted towards machine learning, written in C++ and accessible via Python. There are two simulators in Lightning family, Lightning Qubit and Lightning GPU, ensuring you can simulate large workflows quickly, whether you are using GPUs locally or running on supercomputers. In addition, Lightning integrates seamlessly with Pennylane, providing cutting-edge techniques for quantum optimization for the truly fastest quantum machine learning workflows. So we see here some information on that. It's basically written, it also says it's written in C++, which is a very performant programming language because it is a compiled programming language. So you basically take the code, it runs through a compiler, gets translated into a very efficient machine code, which can then be executed right away. Whereas Python is an interpreted programming language, which basically means it gets kind of live translated by the machine while the machine actually goes through the code line by line, and that kind of slows down things a little bit. But you can basically combine both, so you can kind of write your superstructure in Python, and then the actual execution happens in the background in C. That's, for example, what most of the like Python-based machine learning modules are doing nowadays. Also, if you do like high performance computing stuff in Python, I think it's mostly like this. You basically define something on the front side, and then in the back end it gets executed actually by something faster like C, C++. And we see the same thing here with the simulator, and it looks like it can also run on a GPU. So that's like probably nice to hear from NVIDIA. Then there's some educational stuff here. So there's the code book. I think this is actually a really nice resource. I've been skimming across this. I didn't go like through every single chapter, and maybe if we do like a tutorial series on Pennylane stuff and quantum chemistry, I will. But actually, as I mentioned before, I think these are very beautiful illustrated examples here. So you go on any one of them that you are interested in, and you can really see, like, you have on the one hand the whole matrix formulation and everything that a quantum physicist needs, but on the other hand you also have these very nicely, beautifully designed graphics around everything that explain the concepts. So I think among the educational material that I've seen so far out by quantum computing companies, this is probably one of the ones that is from an aesthetic point, just like looking at it, one of the most pleasing ones for me so far. And if somebody from another quantum computing company is watching who also has educational material, of course, as per usual, let us know down in the comments below. I'm very interested to learn more about what you guys are doing. Back to the main page. So then there's something here about photonics, building quantum computers using photonics. So I think that kind of explains the concept, how things are working, and it points out some of the, let's say, probably important sales points here, right? The unique advantages of photonics. So it works at room temperature, which is very different from what we've seen before when we look at things like ion traps, where the ions really have to be cooled down to low temperature. When we look at superconducting qubits, those go usually in a cryostat. So the main setup is, in these cases, the cryostat, or for the photonics, you also have a lot of lasers, of course. Then it says something about manufacturability. So like how to produce those. I guess that also goes down to like these microphotonics, where you use like the same techniques to build microchips, but actually for photonic applications, but I'm not sure here. Then there's error correction flexibility, modular and networkable, okay. Fast clock speeds, because now here we are working with like pulsed lasers, so we can go really fast. Usually there's like things like femtosecond lasers, picosecond lasers, things like that, which can also be pulsed, I think, pretty quickly. So that's like building on decades of research in creating lasers. And then it also says like telecom compatibility, because essentially, I guess, the light signals, they travel via fibers, and fibers are something that is already being used in telecommunication today. So that's why you can probably combine both. So who knows, maybe you can even have two quantum computers talk to each other via normal fiber connection, and thereby scale it maybe also in a different way. Okay, then it says measurement-based quantum computing. That's probably explained here. And in case you're interested into like diving into how that actually works, like the details of it, again, as per usual, let us know down in the comments below. Then we can take this specific example here and really like do a deep dive on the specifics of how that actually works. Here it says millions of qubits powered by light. So that's probably like on the scalability side of things. There are some publications and another explanatory video here. They also seem to have a community, which I guess is like evolving around the whole coding side of things, because usually when you start to create a software environment, it also helps to have a community which is looking at it and sharing if they run across some issues. So you see there's like a forum to exchange with each other. There's the code book that we've been looking at before, research, blog, and also videos. Finally, there's something about the company. There's a swag shop. Let's quickly check that one out, because I think that's also interesting. So you can buy a lot of very nicely designed different swags here, including this baby onesie. Very cool. I like that. By the way, would you be interested to have School of Quantum swag? Please let us know down in the comments below. Lastly, let's quickly take a look at the About tab of the company. So their mission is to build quantum computers that are useful and available to people everywhere. Founded in 2016 in Toronto. We have here 240 plus people and 275 million plus US dollars in funding. Here we see the different investors. And yeah, I think it's a quite renommated list of people, but of course when you're talking about these numbers, then okay, you cannot have the super small and unknown investors, right? There's another video here, some featured articles. Then we see some pictures. Looks like they have a really nice view from their office. Looks like they have a lot of very complicated and fancy equipment in their labs. And then, yeah, there's here the link to the open positions in case that triggered you and got you interested in the company. With that, I think we are already at the end of this little video. If you liked it, please make sure to give us a like. And if you don't want to miss out on the next one, don't forget to subscribe. As always, make sure to stay hydrated and see you in the next one. Bye bye.